Hello, folks. 我是王不老说半岛. Today, I would like to continue my topic about the packaging process technology. Today's topic is electromigration in advanced packaging. I call advanced packaging AP, especially about its reliability and design and process tips that are related to its electromigration, tin diffusion, hybrid bond interconnect, and talk about companies like TSMC, Besi, wafer to wafer, and die to wafer bonding. These are all related from the perspective of electromigration. Let's begin. Before we begin, of course, I'd like to have some interesting icebreaker. Wish you enjoyed it. Today's icebreaker is Blowing the Wind, Bob Dylan's song. I think you remember that. The answer, my friend, is blowing in the wind, is the famous phrase for that. This phrase is very ambiguous. Right? The answer is so obvious that's right in front of your face, or the answer is as intangible as the wind. Well, that's the famous lyric. He wrote the song, around 20 something, and then become one of the most famous song for it. I like it a lot. Hope you like it too. Why I mention that blowing the wind as my icebreaker thing? Well, because it happened to electron. Electron blowing the wind cause havoc. Electron wind, okay, which means that you can imagine that the electron flow in these directions. It could cause the ion to move around. All right, that is very interesting. Okay, the current flow this way means that electron is moving this way, and it would kick. See, it's kicking. The electron will kick the ions in here in some places, and then force this ion to move forward. All right, net to move forward out of its original place, as if the electron are wind, and this is kind of dust, kind of leave on the ground, and it will follow the electron wind. And that's what I meant by electron blowing the wind cause havoc. And this is called electromigration. It happened in the regular CMOS process, especially at back end line in terms of copper technology. The metal line, many of them, because high current going through it, the very high current density going through it, you will have this electromigration phenomenon. Of course, we are dealing with, our topic is for packaging, right? Advanced packaging. And for the advanced packaging, we see similar problems with a more complexity. The reason is that you can see that it doesn't matter if it's 2.5D or 3D, you see many different materials, different substrate, right? Different technology that form different diet, logic, memory, MEM, RF, and then they connect it with interposer or something else, or bomb. So the electron or electric currents or electrons will go through, many different materials and that different even temperatures. So this electron migration could be interesting. That's what I can say. And so I say the advanced packaging is kind of messy. It's very hard to predict how current will change the material in what way, and that's very critical. At the same time, you need to make sure that everything you do here will have 100% yield, because the assembly line, no matter where you do it, TSMC or elsewhere, you are getting your chips from many places, like TSMC. They want to SRAM, right? You probably gonna buy it from Samsung or SK Hynix, and you will probably want to man meter. You probably get some chip from elsewhere. And TSMC probably can make a logic for you if you agree with the price. And what they can offer is interposer and put everything together. But they have the same problem. They're going to deal with multiple materials. So electron flow through these many, many different materials, different foundries, from different foundries with different interconnects on different substrates. So this is so complex. That's the reason I say it's messy. And so you will see where the bottleneck. So everything we're concerned is about the interconnects. That's where we are focused on. That's where the problems are. We're assuming everything you put it here are perfect, 100%. It's called non-good die. You test it. All this die has been and tested and meet your expectation, meet the spec that's given. And before they even put it on the same platform, right? And that is given. And so you're more concerned about interconnects. And let's look at for the interconnect, you're worried about the current density. Okay. So people are working about the AI packaging. What is the current maximum current density that should be considered? And today, if you look at the hottest power consumption by an NVIDIA Hopper H100 is about 350 watts. And when you put couple together, it goes to 1,000 watts easily, right? And look at how much it costs. See, it's $35,000. And do you remember when I talked about last time how much it costs for TSMC to manufacture? And that's my previous talk. I have given a clear estimate about how much NVIDIA is per chip, per die. Another complete package, just the core logic die. I take it is about $600. Here you have a few of them, that's it. And then you have the periphery, other stuff, the HBM and all that. And you got selling for $35,000. That's the reason NVIDIA makes such a huge profit. And then I'm happy for the engineer there. They got a huge bonus, their options going to the roof. And then they put cash to buy $1 million houses. Yeah, it's happening, right? But at the end of the day, you can see that what I meant is that you need to make sure this thing all works. You had to have 100% yield for each one you put it on. Otherwise, the logic is $600. This may be $20 or $5, whatever. A bunch of things you to put it on, and all cost money. So you better have a perfect package come out that's 100% yield. Otherwise, you will lose big money, and NVIDIA won't pay for it, right? If for the die or the package does not meet the criteria, either performance or reliability, they will not accept it. Then TSMC will lose a lot of money. So the whole thing will lose a couple $1,000 easily, right? So that's what I meant that for the advanced packaging, you have to really worry about all the intricacies between that when the current goes through it. You got to worry about that, make sure they're all perfect. They're all exactly what you want and no problem, including electromigration. Okay. And then look at when we work on the package, we draw the learning from the regular CMOS. So you look at the CMOS, what is the maximum current density according to ITRS? And that's what you're looking for. And people done that. And you can see that the order of magnitude, okay, is changing from 10 mega ohm, 10 mega ohm, 10 mega amp per centimeter squared from 10 to 1. This is 10. Okay, this is 10 mega ohm, 10 mega amp, right? And then this is 1. So electron migration, you are going to see the problem. You're eating into this. this yellow bar is 10, roughly 10. The yellow area is 10. And you're looking at to 1, okay, here. Yeah, this is 1. So we are going to that. In the year right now, people are talking about anything in 1 mega N per centimeter squared. You are worried about that, right? And then the line width is reduced 10 nanometer because this value is simply because scaling, not actual current, but current density. Just keep that in mind. Earlier they were 10 because in 2017, but in about 5 years, you drop down to 1 million M per centimeter squared by tenfold. So that's what the concern is. Electromigration in this aspect is that the electron wind will blow the copper here to the right and will leave a void here. And of course, that will make this, it will have a broken line here. Then the device is dead because the current cannot go through it. And this T50 is the reliability measures, right? So all these are some kind of a metrics to describe the JMax versus the JM, the electromigration. And we had this for the regular CMOS, but we don't have this for packaging yet. I don't see any report on that. If I see it, I will add something to. Right now, it seems these fields are still only a few players. It's not like copper that everybody back online. There are tons of research going on at the same time. They have this clear trend. Right? They have a lot of data, and that could clearly show them the trend. But they cannot do that in the advanced package. Nobody will release that, right? Only TSMC doing great. The other one is limping along. And then there's only a couple of companies doing that, right? Other company, Intel, Samsung, OST, and all that small scale compared with TSMC. And TSMC will not tell you, right? They say, oh, it's okay, no problem, don't worry, right? That's what they will always say. And so do we have equivalent JMax trend for the advanced packaging? Nope. Okay, not yet. Maybe in the future, maybe. But can we learn from that? Oh, yeah. So that's the key. We learn from the CMOS process flow, and we will apply that to the packaging work. So my proposal in this talk is this study electromigration and reliability for CMOS device before moving into advanced packaging. So that will be the approach of my talk. Okay. And this is what I meant, right? The electron blowing the wind. I introduced this one for you. Say it's the electron flowing, and then the copper ion being kicked out. Okay. And then, well, there's many forces. Electron blowing the wind, there are many forces. The electrical force on a diffusion atom, there's in here, in this example, it's electron and then the wind, electron wind force. Electron wind force and then direct force. Okay. The wind force and then the electron is this EL, electrostatic force. Yeah. Yeah, force that may go with it or go against each other. Right? And the electron wind force, as we say, blowing the wind force at the same direction as electron flow. So at the end of the day, most likely electron wind force deplete the ion in the direction of electron flow. So that's see the electron. But this is opposite to the current flow. Keep that in mind. This is electron flow. So this one will move forward, right? Yeah. So this one, as shown here, that the current going this way. And then in the same direction of copper going this way. But is that happen to all the metals? Not exactly. Be careful. Let's be careful. Okay. And what's happening then? The electron migration will result in Hillock and voids. This is what I meant. Hillock is like a hill that would make, see here depleting, right? So this atom moved to here. becoming extrusion, running extrusions, or it will disappear. This will disappear, and then it was lying here. This is kind of a void, so it's kind of become an open or a short. Here you touch the other metal line, become a short. Okay, and clearly see here now where. So question is, where is the direction of wind flow? Obviously here. Okay, so people can ask. I'm still talking about CMOS right now. There are three metals being considered or being used already, of course, in the back end of line besides tungsten. Is copper, cobalt, and ruthenium. All these. And which one, I will ask a question to you directly. Which one is more electromigration resistance? How can you tell? Right? And then the people say, oh, it's because whoever can move easily will have a higher EM tendency. Well, what do you mean by EM? They move easily. Well, that's indicated by the melting temperature. Okay. So the activation energy from metal diffusion is just proportional. Your activation energy is proportional to your melting temperature. That's it. Okay. And people even come up with an approximation of 38 or this number. And people calculate it. It's 2.2, 2.9, 4.2 for copper, cobalt, and ruthenium. This one has the highest melting temperature. It's a precious metal, right? Just like the platinum ring, you bought it for your wife as a wedding ring. If it's white gold, that means that the platinum, that white gold, meaning that is platinum that actually combined with ruthenium, right? To make it more malleable. And you can see that the ruthenium has highest activation energy for diffusion, meaning that it will have the least amount of probability of electromigration, which happen to be true too. But these are not that useful. You know why? Because we need to know what is the true diffusion activation energy. Here is a bulk, okay? It's a bulk. We need grain boundary and all surface, and that's more important. Right? So you can see from the research, you can see that the grain boundary diffusion is much less than the bulk. For ruthenium, it's 1.8 versus 4.2. So it's because ruthenium movement in the grain boundary is a lot easier than in bulk. Surface diffusion even easier. So people have done the research on that and find out rutheniums under certain condition, you will still move around, right? So at interface, okay, grain boundaries, or you need to be careful. Be careful. So, but people, the beauty of the CMOS is that there are so much resources putting on to understand the diffusion of metals because of electromigration. And people come out with these universal grain diffusion coefficient formulas. Yeah, so lattice is the bulk. All right, so it's 34 Tm versus RT divided by RT. The R is the gas constant. Grain boundary 7.8, that's 1/2. And the surface is even lower. So the lower the value of activation energy means it's a lot easier. So right now, people focusing on the grain boundary because the surface has been kind of protected and they were covered by something. So you pretty much don't have the surface diffusion anymore unless you're exposed, then you have a problem. But usually they're kind of capped. They're sandwiched by adhesion layer, diffusion barrier there, all kind of layer that protect the metal of interest from exposure to oxygen. And so people mostly focus on grain boundary diffusion. And here it's 1/2, roughly 1/2 of lattice. Is it 1/2? What's the big deal? Oh, it is a big deal because this exponential equations, 1/2, meaning that's orders of magnitude faster. So let's keep that in mind. So, and so if you look at aluminum here, it migrates by diffusion most of the time. Okay, 0.6. You know, this is the dominant one because lattice is 1.4. So you know this is dominant one. But copper migration of surface in its grain boundary. Its interface is small too. Okay, grain boundary 1.2. And it's much less than the 2.1 lattice bulk diffusion. So copper are different. When you mix two together, they are also different. Right? So that's why I meant here that aluminum migrate by only the grain boundary. That but copper are different. Copper are different. They will like the grain boundary interface. They all like that. The lattice probably not. Don't worry about that. Surface, okay. Then surface once exposed is very bad too. This one and grain boundary interface. All these three are critical for copper. But when you look at the electromigration, are you telling me that electromigration is the only suspect for voids or extrusions, right? Even at high current density, mega ohm per centimeter squared, as we mentioned here, and it's getting close, right? It's here already. If you operate in this range, then you will be in trouble. Okay, you have to worry. And this thing, when it start to change around and form this way, is if people go, oh, that's electromigration. But what do you mean by electromigration? They form voids, they form the extrusions. Are they the real thing? Let's put that in perspective. Okay, let's look at this a quick summary again. So when you see electron current going this way, meaning that the electron current go this way. This is regular current. This current go the left side, electron current go that side. Then the atomic flux due to electromigration will move with this. But the vacancy due to stress will do the other way around. So atomic flux is the opposite. So the stress come into play now. Well, that's not just the electromigration, right? Stress also come into play. All right. So here in this example, that just pure migration, pure electromigration. Then here you have the void, and here you have extrusion for potential shorts. Right. What I meant is that deciphering electromigration failure is tricky. There are actually three driving force. Here we introduce additional force stress, right? But actually there are three. Three driving forces at play. Electromigration is dominant at high Jmax. Thermal migration, right? What I meant of thermal migration is the thermal gradient. If your circuit has somewhere hot and cold too much, the contrast too much, there's a thermal gradient, like the edge, then that place could be vulnerable. Or stress migration, which is there's a stress differentials. You cannot see them, but you can feel them for sure. And the failures you see are caused by all three forces above. Electromigration is usually dominant, but at the same time, this one should not be temperature sensitive, but it is sensitive to high temperature. All right. It's supposed to be very sensitive to current, but it's sensitive to temperature too. The reason is that the atom will move at a higher temperature. So this means that if you look at the data and say, oh, it's caused by electromigration, you overestimate the T50, the reliability matrix. Be very careful. Okay. And people, especially Professor Took in this area, did a very good summary in his book, which I like. Right? He had a unified model for the mean time to failure. So he has this three formula for you. This one is a famous flex equation. And the thermal migration, as I mentioned here, he derived that you have the thermal gradient. And the stress migration, you have the stress, okay, gradient. It had to be a gradient, by the way. No gradient, then there's no driving force. So very careful with that. So, and then we'll talk about the Black equation later to explain what's going on. Okay. For induced back stress reverse the electron, a back stress. This back stress happens during your electron migration. You're moving an atom, right? The atom moving around, it will feel the environment. There are other atoms around, you want to move. The other atoms don't say, no, 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 you cannot move. I'm here. You're the new guy. You are illegal alien, okay? By the way, don't come. You push your way through, and then you will feel a strain. So, and that strain will drive the ion in the opposite directions, as we mentioned here. Okay, the atomic mass is go the other way of the electron flow because it's simply because of course that so it's just the opposite because they go against the nature, the direction of whatever you want to do. There will be counter-interactive force go against you, and that's induced by the stress, especially the stress gradient. All right. And with that, people actually figure out there's an interesting the Blanch lens product, which means by make the flux go zero, right? This formula that we introduced here, make it go to zero, then we arrange the equation, then we'll get a lens, all right, times the current. It's a critical lens and current relationship. If you are less than that, all the net flux, the atomic flux go to the left, will equal to the from the stress is equal to the atomic flux to the right. So this one cancel out, isn't it? Cancel each other out. And when you cancel each other out, then the then well, that's great because if you design your lens less than this one, this value, then you never have electron migration issues. That's the beauty of it. But whether you can do it, actually design your lens that way, that remains to be seen. But designers should keep that in mind. There's if you do it right, that meeting these criteria, then the void will not form. Put it that way. Okay. But if you want to compare, the besides stress, the thermal gradient, people done a wonderful experiment. Yeah, say, oh, what about electromigration by the thermal gradient? It turns out even the force that from the thermal migration compared with the force from the electron migration. This is the electron wind. I'm talking about the force here. These are all the forces that I could induce you the force. The force is the equivalent charges times the field. That's what I meant by the force. So there's electron wind force. We're not talking about electrostatic force yet. There's an electron wind force, and then there's a thermal gradient force. The thermal gradient force is two force on this force, thermal migration force. Even though this experiment shows that the force is small, that equivalent to 6 eV per centimeter, it's much less than the electron wind force, which is 40 electron volt per centimeter. Sorry, it's not the not per meter per centimeter. Then you would think that's not important because the activation energy or the force from the thermal gradient is far less than by electron migration. But according to experiment, electron migration lifetime shortened on the effect of temperature gradient on the electron migration induced failures. Okay. the gradient will cause local failure faster. I would call it adding salt to the wound. This kind of phenomenon. It's very weird, but really interesting at the same time. So what I meant is that, this is what do I mean by that? I meant that electromigration, thermal gradient migration, the stress migration, they interact with each other. Electromigration is driven by the momentum transfer from the electron. All these three things, electron migration, thermal gradient migration, stress migration, they all moving the atoms are moved in maybe in different directions or the same directions, but for the reason of their own. This is because electron flow, right? Electron wind blow them. They just blow by electron. Electron pushing these atoms forward. And the thermal gradient, because the atom want to move from hot to cold, because of temperature. Are they the same direction? In the direction of electron flow as electron migration? Don't know, right? It's material thermal conductivity and thermal gradient. Tricky. This is tricky. And stress, right? That it wants to move because your atom are moving forward. You change the environment as it happening, and that stress is pushing back material from its intent. The electron wind want to move this way, thermal gradient want to move from hot to cold, but all these are going to face a stress resistance. And all these forces are interacting, influencing each other. So that's the key message I would like to convey. And so when you have these three forces in mind, the next step is, okay, what tool do I have to analyze them? And here I'll introduce the reliability. Reliability is prediction of failures, right? It's a reliability engineering business. Two popular tool is in electromigration perspective. It's called whiteboard analysis and Black's equations. These are two key tools when we're facing the electromigrations. So what is a whiteboard? Whiteboard is a person's name. It's a colonel. It's pretty smart. He figured out that any machine part, any machine that you create, would have reliability, the failure rate versus time, like bathtub. Initially, you will see a very high failure rate. It's called infant mortality. And then you will quickly going down. And then you go to a long, hopefully long enough period of time that's where your warranty is, right? Like you're buying any cell phone, you say at least 1 year. They give you 1 year. You buy a Costco, maybe give you 2 years. So normal use, hopefully that failure is very low. And then when you use it for a long time, you find your machines getting slower and slower. You know, it's not as bright as before. It's a wear out. Eventually, you're gonna die. So all this bathtub curve, right? Weibull, he figured out a unique probability density functions. PDF. It's not a PDF that we say PDF file. No. This is probability statistics. The slogans. There's PDF. It's called probability density functions. He used a function to predict this funky curve, the bathtub curve. So he come up with these functions. All right, it's a beta, eta, tau, and all that. With some exponential here, with this power law here. That's his genius. And it turns out he says that this curve can be predicted by beta pretty nicely, you know, with some value of tau and gamma or eta. That's actually secondary. The most important is the shape parameter. Say the beta is, if you have less than 1, is this part, this part. And beta is equal to 1 is this flat part. And then the beta is greater than 1, greater than unity, that's flat part. So if you could do experiment and figure out these values, you are done. Let me give you examples. For example, I use other this is GaN devices or hybrid drain, GIT, jet injection transistor. It doesn't matter. Some devices. I'm doing some experiments at high temperature reverse bias. So I put two stress on this device. I put a higher temperature and then a higher voltage. And then I look at functional time, how it behaves. You can see that this part has no, this device, there's no early light failure, doesn't have that. But obviously it has this curve, right? This curve, it goes up, fail. And so it depends on the temperature and the voltage. I'm accelerating the failure modes. So question is, which part of Y volt best of interest? So here you can easily see it's measuring this, right? You can measure this. From this data, you can calculate your beta value in here and in here using this formula, right? It's easy to derive that. There's software available for that. So you don't have to worry about that. You just need to know from our process engineer perspective, what does this mean and how do you get it, right? So that's people do. And pretty much, so in a summary of the spec, and then people generate a spec according to that. They generate a spec for viable according to this. See that? It's called JDEC, right? JDEC will give you a test to see whether you could avoid this and avoid that. And the flat part is random failures, meaning that the failure are random. Every machine has a random failure, and it's part of the nature because of temperature, because of use. And then later on, you will have wear out. That's because the parts, so like a car, will not run forever, right? I'm talking about if you don't do a maintenance, you will fail at some time. And hopefully you could extend this constant random failure as long as possible. This window can be as long as possible. Like Toyota is more reliable than the other car, and then they have a wider random failure. And then you may have some stupid car that fail quickly. That will be early infant mortality. You bought a new car, you fail in 1 month. That will be early infant mortality. And so all these will be in your JDEC spec. This is a spec that people use, and you could easily find them. You could easily find them in the in the documents. So as I've shown here. Oh, here the ADC document. All these documents. See that? Wow, tons of them. Wild bond, shear phase, human body model, all kinds of tests. That you will see that. Let's click one. This is a failure mechanism-based stress testing for discrete semiconductors. Okay. Now, if you click that, it will give you some spec. All right. That's a book pretty much. And then you go through it and you have to do some tests according to what's given in this test. This is defined by Simon. You have to use a proper test method to go through that. All right. And so this is for not just gallium nitride, but for everything else. I'm just using it as an example for you. Give you a more detailed example like this, right? So the JDEC, the JEP 100, 180.01, here is the guideline for switching reliability for gallium nitride power devices. And you can look exactly what they want you to do. These are conditions and examples. And then most likely here, so this is the temperature I want you to do, 80 degree to 125 degree, and a certain moisture. And then I want you to do something. And then this stress name, that dynamic high temperature operation life cycle. Okay, operation DH toll. And you have to do, this is a number of lots you have to do. Each lot is 8 tests. And you do 1,000 hours, no failure. That's criteria, zero failures. So this, you have to follow the guideline. And then once you finish the guideline, then you could talk to your customer. I met the product I made for you, met a spec of JDEC, JEP 180.1, or they will actually assign a spec for you to meet. And why high temperature are required is where the black question come in. Let's use a quick example to show how much time we can shorten if we raise temperature by 30 degrees with 2x current to predict a lifetime of wire with TF 5 years with your time to failures 5 years at 85 C. All right. This means that so we want to test the parts that supposed to be survive 5 years at 85 C, but we don't have 5 years. And how do I know my parts right now? I have a shorter time to meet the spec can meet this criteria. Well, say you increase the temperature by 30 degrees, you increase the current density by 2x. And by using this black formula, right? All these are known. And it's like 2. Activation energy is material dependent. And here is 0.18, 0.48. So I put this number in. The 5 years can be reduced by about 8 times to 5,000 hours. This is just to give you an example that if you increase the temperature, say, how about not 30 degrees Celsius? I make it 100. How's that sound? Well, then you come to here, right? You could do the 125. And then the spec says that's 1,000 hours. No fail, all right? This is actually what they want you to do. You need to put the part in the oven 1,000 hours at this temperature without fail, right? And same thing here. So here, if you do that, I bet it's not going to be 5,000 hours, much shorter. And you do the test and you meet the spec, you say, oh, I meet your spec, collaborative spec. But do you think that's the only formula that people use? Well, not exactly. There's many derivatives, right? The equations, people use this form. The form is exponential term, and then it always exponential term or power term. So you can see that in this mean time to failure, this formula they use, and they would look at different temperature. It turns out this test is not sensitive temperature. The EGAN, that a specific product that I'm presenting here, that EGAN, good, it's not sensitive temperature. That's very nice. And the 10-year meaning that they have to meet the spec. Right? Extrapolate here and go all the way down. They will meet the spec. Okay, that's what they want to do. And this is great because they find out that activation energy is close to 0. See here? Close to 0 meaning that it's not sensitive temperature at all. So you can put a 0 here, this term becomes 1. But it's very sensitive to the beta value, right? So if you look at the more detail, you can see that exactly what the JEP 180.01 is trying to ask you to do. There are many different tests. HTRB, haste, TC, thermal cycle, temperature cycle, power cycle, high temperature storage life, all these. See the temperature here? 150, oh my God, right? And the bias is 480 and 1,000 hours. And then the sample is how many lots and samples that you need to put it in. 230 samples, all right? That's what they want you to do in order to meet the statistical minimum limits. And all has to be 0 failure. If you didn't have that, you fail. Okay, that's how stringent it is. Okay, and the other one, the spec is like that. Oh, they have other criteria here. You can look at the criteria here. This one, VGC, 7 volts, but 1,000 hours, right? And here, 150C, the bias minus 12 volts, 1,000 hours. And here is a 480 volts, 1,000 hours, but with a humidity. It's humidity The humidity test, meaning that you need to resist the natural environment, the harsh one, in a proper way. Right? So all these have to be done and all has to pass. Zero failures. Okay. And it has more complex form now. So even this from this EGAN from this company has a different type of uh, a little bit of different type of the MTDF. They are all derivative of the Black's equation. The Black's equation is what I've shown here, this one. They all have a special their form. You just need to figure out, you do the experiments, and then you figure out what the form should be. These all can be done in software very nicely. It's not difficult. And you get your values accordingly. And all these values give you a property of the material of interest. Okay. Now with this knowledge, let's move on to CMOS reliability, right? And we, as I said here in the beginning, they study electromigration and reliability of CMOS device before moving into the advanced packaging, and that would be my flow. So with that, let's look at the aluminum. This aluminum has been used in the early day of CMOS. Wasn't right now? It's not copper. Nobody uses aluminum. Yeah, you're right. But this is important. The process learning is always important because that's what process guys do. They need to know all the material, how they perform under different environments. That's what they do all day. Aluminum is important because there's many process learning that you could port it to packaging, even though packaging may not be using aluminum. But the message here is that aluminum is a low melting temperature material. It melts at 660 degrees Celsius. And tin, one of the ball bonding solder material, very critical, it melts at 231 Celsius, right? And then there may be some learning you could pick up there. That's exactly what we're trying to do here. A quick summary of that. If you treat your metal with some kind of plasma, so you oxidize the plasma to make it natural, the surface state become a natural aluminum oxide, which is make it strong. Just like you're buying the some cookware with anodized aluminum on top, and they claim to be on stick and all that. It's become a better material in avoiding electromigration or something. So these people propose to do that, and this plasma trick is very helpful for your toolbox. Right? Every process engineer need to have a lot of tools in the toolbox. The more tools they have in the toolbox, the better off they could solve a new problem, the unforeseen problem. And also the argon plasma. So if you perform on the tie underlayer, your electrical lifetime is improved by 1 order of magnitude. So if you this aluminum has a tie underlayer beneath it. So if you treat that nicely, right, you give it oxygen, then you make surface so clean. The bonding between aluminum and tie is so good that improve the EM lifetime. And if you deposit aluminum copper in a pure argon, well, it's good, meaning that it's not oxygen, right? Has fewer oxygen atoms to make your surface bad. Oh, if you anneal it, 430, 50 degrees Celsius, 30 minutes, you form certain compounds with a higher electromigration activation energy. So this aluminum 12, tungsten, something like that, right? So all these maybe. So this give you an idea. Anneal helps, and that is key, right? So this means that this proper anneal, it may not be happening for your packaging, but it could be an idea that it may not be the same temperature or the same time duration for the anneal, but the idea of forming a compound make it stronger, stickier in a sense. the higher electron migration energy, then your EM will be better. Or lowering the dielectric temperature. Wow, that's interesting. So here there's a lot of dielectric here. Here, dielectric insulator. And if you lower the dielectric temperature, and then the resulting thermal stress will be less. That's what's that's been found in this example. That help to help your electromigration because it's a less thermal stress. Remember, we keep mentioning the three forces, right? The three forces at work, three forces in the electromigration failure. They all kind of interact with each other. This electromigration, but typical black or thermal migration or stress migration. Stress migration usually meant thermal stress. Okay, so this is a thermal stress item, and that's the reason people say, "Oh, how do you do that?" Well, the relevant part is that the electric temperature here, and this the electric one actually improve your EM if you do it right. This means that electromigration will see its neighbors, how the neighbor build their houses. You can put it that way. And of course, barrier layer, nitride really help. All right, all these learning are important. Well, when you put this learning into your advanced packaging learning, you know that everything is important. Your neighbor is important. All right, your underlayer, your body that connect these two tungsten here is important. Everything is important. Don't focus on yourself only. There are other things to worry about. Okay, so this is design tips. So what about the design? I'm sorry, this is a process tip. So what about design tip? Oh, here you can see that. If your current, which one is better? Let me ask you, which one is better? It turns out, obviously, if the current go to this way, meaning that it go to three places, but if the current go it's opposite way, then most likely this one will get most of the current. And this one will create a local hotspot due to Joule heating. This one will somehow heat up. When it heat up, by local hotspot, electromigration going to be degraded. The performance of electromigration going to be degraded. So if you are a circuit designer, you want to do this. You don't want to do this. You make sure your electron current don't go this way. Right? So this one you cannot see, but that's like learning, right? And what else? The cap layer. Cap layer, there's something to cap your copper is important too. The cap layer, the form of good copper compound is here. They introduce all these different copper layer, cobalt, tantalum, tinitride, silicon carbide nitride. They all give you very different forms, right? And then these different temperatures. So this one you need to keep in mind. Yeah, here is a 352, here 253. Yeah, all these material. And the cap layer is very important. And currently, mostly people like this silicon carbon nitride, SiCN. Then what else? You are getting a new material, right? Yeah, that's part of the process engineer will recommend when designer goes to them. And so, well, let's get a better cap that it. And this learning from the CMOS has been done, right? And what else? Oh, here is an interesting one. It's called the reservoir lens. The reservoir here has no current. The current go this way, or vice versa, or this way. Doesn't matter, right? But this part has no current, no current. But this part is actually important. Why is that? If you have enough this part, then if you have somehow a local, for some unknown reason, there's electromigration happen here, then the reservoir will feed into it. All right? It's kind of sacrifice. It's seemingly useless, but improve the electromigration by supplying atoms to the void area and delay the failure process. I call it it's a design for manufacturing at work, DFM, design for manufacturing at work. It's an idea like a CMP dummies. CMP dummies do that. In CMP standard typical process flow, you want to create a lot of dummies, which is useless. You are not connecting to anything, but it will help you to improve the within wafer non-uniformity. You will make your circuit, the copper area, do not have less dishing or erosion problem, which we're going to talk about later. Okay. Here, these are all learnings that designer, if you have the luxury, please add some reservoir. You will make this corner stronger. All right. And this one already introduced the Bletch lens product. All right. This product, if you design your lens right, this is a derivation of that. We show it earlier, right? We show it already that this is the gradient on the stress. This is from the electron wing. If there's a net flux is zero, then you got this the Bletch lens product relationship. You might never have an electromigration issue if you design your line right, make it less than what this product can be. That's a critical one. I'm not sure if you have the luxury. That's a key. You calculate, say, oh, I can only have lens like 2 micron. Well, sometimes the circuit, the chip is so dense, you cannot have 2 micron, right? You have to have different widths of lens. And process tip to improve copper electron migration here, I forgot to introduce that, sorry, is a better copper cap interface. Here's an idea. The interface is important because in this example is the defect generation in the mandatory CMP. When you have copper that deposit, you need to polish it down. But if you don't do a polish properly, the defect will be formed after CMP, and you don't clean it, plasma clean properly, then you're doomed. I mean, not doomed, you will be very susceptible to electromigration. So interface is important. It's very critical, especially some defect form. And you can see that with different treatments, they're very different. You have the in situ. So what people do is to optimize plasma clean, right? In situ means that when you are the wafer come out on CMP before you go into the other step, in that step, you do in situ clean before you really do your cap layer. You want to put a cap layer, like silicon carbide, SiCN, and then before you do that layer, you have to make sure your copper are super clean. So you could do in situ clean, H2 ammonia clean, or helium salt spark clean, is to remove the native oxide of copper. So that's important before you cap it. So that's critical. Right? And then, of course, the liner is important too. The copper has good liner and barrier. And then how do you do the liner and barrier? It's just not going to deposit whatever you want. It's not that simple. Right? For the aluminum and high nitride barrier system, you need to break it. You need to intentional vacuum break before the aluminum gets deposited. So you do the liner, and then you move the wafer into aluminum or copper chamber. You need to have a little bit oxygen. See, this is funky stuff, right? So this process is just so interesting because a little change will change dramatically your electromigration in terms of the process. In a copper one, you don't want it at all. Okay, the air exposure right before copper is very bad because copper, when you see oxygen and get it, it's going to be nasty. Copper oxide is very unstable. And of course, grain size really matters. All these are your material or the process. These are the gimmicks in your toolbox you need to master, right? you better know everything in the world, how one material react without your. Sometimes you need a vacuum break to see some air. Sometimes you don't want it, and sometimes you need essential clean. All these are interfacial engineering is super critical for our CMOS world, and every guy had to learn the hard way. Right, even the Q time. I learned all Q time. The wafer cannot travel so long. Maybe if you put it in the food system for too long, it oxidizes and you don't. So there's a queue time limit. But the queue time will keep the operation a lot of problem. They need to move the wafer in a faster manner than the not queue time, the lots, and not create a problem in operations, right? So all these had to combine. You had learning from this the old CMOS world, and you could put it into the new world. So let's move into the now we can move into advanced packaging from electromigration perspective, right? And let's look at that. The idea is that the porting all the knowledge from the CMOS learning to advanced packaging is given. It's given. But there are additional consideration you need to consider. For the advanced packaging means that the pitch is under 10 micron. And you have a tighter 3 sigma control everywhere, many places. And it's already close to the backend line right now. All right, right now it's nanometer in the say metal 1, metal 2, metal 3, right? But in the backend metal 5, 6, 7, you may have a micron pitch already. So the advanced packaging these days is going to 10 micron or less. And it has additional constraints. What do you mean by that? Well, you need to have a very low defect density because remember, anything you connect them together are very expensive stuff. If your interconnect are dirty with a lot of particles, then you're going to lose the high value parts you put it on. And usually temperature are low because you cannot have your dies that already pre-manufactured good long die to withstand high temperature. Anything above 500, about 480 or something like that, you're doomed. You cannot have that high temperature. Then that's a consideration because the die on top will die or will be dead. So you need a lower temperature and very high throughput. By the way, you're putting many things at the same time, and you better have high throughputs. I'm talking about a couple of thousand parts per hour. All right, that's pretty fast. In the regular CMOS world, you don't have that. You don't need to be that fast because they process one by one. A lot of them are single wafer chamber. They're quite slow. Okay. But what I mean by 3 sigma, I look at this. This is the enhanced capability demands for the different platform. Right? The present this FCBGA, the fan out, wafer level fan out, 3D-SI silicon in chip, right? Classical 2.5D, all right, 这个 EMBI, all these have a different criteria, okay? 0.1 to 0.2 micron in terms of accuracy. And then you look at this, the 3D hybrid bonding is getting to 50 nanometer 3 sigma. That's scary. Okay, that means that we are putting things together mechanically on a wafer that will have 3 sigma around less than 50 nanometer. That means every sigma is about less than 20 nanometer. That's scary, right? Mechanically, I'm talking about mechanical, okay? And these are very scary challenges. And then the Besi, the company, doing a pretty good job here, okay? So let's review a little bit about hybrid interconnect because that's where the advanced packaging is about. And you look at its flow. So you can look at its flow from here to here, and then you can see that the whole process, patterning and all that, these are called dual-damascene process, right? And then when it finished out, they bound together. The two wafer bounding together. They went through the electroplating, copper ECD. This is the name of the tool, all right, from the Novalis. No, it's probably name, right? Copper tools is plating. These are plating. And And then the liner are PVD liner. They are not going to CVD or ALD yet, still in the PVD area. All these are dual-damascene process. Dual-damascene is a typical CMOS background line process. And then we're bonding together. And this bonding, see that, had two parts. Why is for hybrid bonding? Because it bond at the oxide. This is SiO2. Okay, this blue one is SiO2. The blue one has to bond properly, and the copper one has to bond properly. All these are dielectrics. All these have to be bound properly, and that's what goes hybrid, right? And as I mentioned earlier, we are getting process flow from the CMOS, and we're going to have the same problem, right? Same copper CMP problem. Here, there's some CMP here. There's some CMP, metal CMP, right? Here, you planarize it. You deposit and planarize it. And when you planarize something, you will have this called tishing problem and erosion problem. Here's a roll off, right? The tishing problem in the select area, this is erosion is here. So here is because of different density, this is about different materials. So they're gonna have different problems. I'm sorry, they have the same problem, similar problem as a regular copper, and it's the same solution. What do? You call dummies for help. You just had to make dummy. So that's the circuit designer need to take this into consideration, right? And so this is where you learn from the CMP process in the regular CMOS. From the regular CMOS, you learn your copper dual-damascene, you apply to your AP, advanced packaging for your HBI, and you have the same problem, you call out the same dummy for help. That's given. But it sees more codependencies. So here, see more material now. He has seen in this example, the advanced packaging see many material geometry, by the way, different geometry too. So here's a big bomb here, and it's a very fine line. This won't happen in the regular CMOS world unless the last layer. But in the middle layer, they won't see that, right? Everybody's same thickness, roughly, same width. They're not going to see suddenly come out with this big bomb. And then different materials. So electron paths see more abrupt changes from among material. Your copper, this copper CDL, RDL. RDL means redistribution layer. SAC, this is tin, silver, copper compound, solar bomb. And then the nickel underbomb, interposer, copper pad. So all these are different material, different thermal expansion coefficient, and different resistance, by the way. And then the shape and thermal, they're all very different. So you have a different thermal stress and mechanical stress because that's how they manufacture are different. And they'll see different environment. Of course, you have different stress. And therefore, it's difficult to locate the hotspot because hotspot is where you're looking for. Right? Because the hotspot will give you the Jmax, and then and you want to make it less and less. Right? You don't want to have locally very hot spot. And this is where the electromigration and net design spec need to see before even packaging process. You need to find out where the hotspot potentially can be, right? And what the packaging best occur from the stress, under stress, all right? A typical stress, they will actually, from the Weibull perspective, initially you may have this flat line. This is what you desire, right? Very low input mortality, kind of long random failure. That's with the normal use. And very small the wear out period. But in reality, you have a stress, some kind of stress, then it will bend down. The whole curve will shrink under stress for each component. This is talking about each component, not just the whole system, but each component. But for a system, it's critical because it's a serious mode. Yeah, you have many devices. A serious mode means that if you any part failure, the whole system failure. And usually event packaging has few or no built-in redundancy. So it's a serious mode. Here, what I meant by that is that if you look at a packaging, typical packaging, then there's no redundancy for your logic, right? Just one logic in this design, you just, I want to redundant, I put two logic here. It doesn't work that way. Your memory has no redundancy. These are all just one, one, one. You cannot afford to have redundancy. That's what I meant. And then, so this means that it runs in a serial mode, right? It runs in a serial mode, and every interconnect, here is the interconnect, has to be success, has to be 100% success. And any failure in these connections, you're dead, right? So that's called serial mode, series mode. The 3D NAND, on the other hand, a little bit lenient on that. We'll talk about the 3D NAND for the advanced packaging using hybrid bonding, all right? And then the varying stress. So as I mentioned here, the varying stress will give you a different curve. Usually will curve out or cringe. Well, this is some of the examples I've shown here. It will move to a shorter time at different conditions. Here, and how do you calculate it? So the EM test is run at different temperature and current conditions to populate reliability model based on Black's law is what you do, right? This is Black's law. Black's law is very straightforward. Let's review that a little bit once again, and then show you the curve. I should show you the Black failure. Where is it? The Black formula. I want to try to get to remind you what it looks like. As we mentioned many times, this is a Black formula with different stress condition, as I previously my example show you. 2x of dry current, different temperature, then you just do this simple mathematical formulation following this example. Okay, so the stress condition, that's what we actually do to predict the future. This is what we need to meet in reality, right? And we don't have that time. We don't have for 5 years or 10 years. Then we have to stress the device in a way. Say, I'm doing only 1,000 hours, and that's equivalent to 5 years. Okay, well, how do you convince me to do that? Well, Black's law, Black's equation show me that I could do that by changing temperature and then the stress or current, and I could do that. Okay, if you agree with Black's equations hypothesis, then you're fine, right? And 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 let's look at the failures. For the solder failure, this is a classic one. Now you can see that, oops, there's a hole here. That even as the electromigration failure initializations, it will always happen here. People find out it fails between the intermetallic compound and solder cathode with electron flow this way. See the electron flow this way, it carry something with it. What exactly carry? Carry tin in this case as a culprit. Why would carry tin, not the other material? You have copper here, you have lead here. Why not? Well, that's because tin has a lower melting temperature. Okay. And what does speculum do? Okay, here's what we're going to see. This reliability test. All right. Previously, we see the other reliability test. This is a JEP 180.01 spec for gallium nitride power devices. I mentioned earlier that's say temperature, high temperature, okay, reverse bias, 480, and then how long you do 1,000 hours, no fail. You compare that to the advanced packaging. All right, here you have JSD22, all right, all these different temperature, the thermal cycle. You have cycle between these two temperatures, minus 65 to 150, and then 30 minutes per cycle, and then 15,000 cycle. And then this is leakage resistance. Failure criteria is resistance. Electromigration change the resistance, right? So, and that's the criteria. So all these are related to advanced packaging criteria and their spec. And then it's all in a JDSD 22, exactly what you need to do. And with that, let's look at, as I mentioned earlier, the tin, in this case, move around by the electron flow. And so it move around, create a vacancy inside. So why is that? So why tin is always the bad guy, right? It moves upward. And this structure, this is your ball structure simulated. Why is the melting? So the question I should ask is that, why is the melting temperature tin versus copper and nickel that's in this compound, in this fluorine compound? Well, tin is 232 degrees Celsius. Copper is 1,084, and nickel is very high, 1453 Celsius. So you can see that if tin's going to move, it's tin. If electron going to move everything around, he like actually, electron like to move everybody, okay? He like to move copper, he like to move tin, he like to move nickel. It doesn't matter. He push everybody around. He's very bossy. He just want to push everybody around, and only tin, in this case, can move, right? And when it moves, it forms compounds. See that? And if you look at this, you guess what is the tin diffusion coefficient. In this case, the intermetallic compound, I'm sorry, this is not forming by migration. This is just because intermetallic compound form. I want to know what is the tin diffusion, right? This is not about electron migration yet. I just want to know what the value of tin diffusion coefficient at 150 degrees Celsius. It's been running for 32 days, 150 degrees Celsius. And I use this square root dt formula. I'm putting this as 1 micron in. I easily calculate it's 3.6 E minus 15 centimeters squared per second. This is actually quite large because the temperature is too low. You will never see this value for copper or nickel. So I will give you a quick estimate. When you look at a picture, that you always see from the TEM and from the SEM and all that, you could clearly see this compound formation, and then you could quickly, using the data at hand, the time and the temperature, you can easily calculate the diffusion coefficient. Roughly, the order of magnitude will be correct. So that's the message I want to convey. And now let's move to the really tricky part. Okay, so this is a classic one. We introduced the classically the soldering part. I now want to focus on the hybrid HBI, the hybrid bonding interconnect. Okay. Hybrid bonding interconnect. That's about the last part of my talk. I'm talking about the wafer to wafer versus die to wafer hybrid bonding challenges and results. This is an IMEC test vehicle for hybrid bonding. And you can see that the cap, see here? Here, the silicon nitride cap is used everywhere. And this is a mature process learning from CMOS. CMOS has that when they have multiple metal layers that have been formed after CMP, they always use SiCN as the pad, as the cap material. Right here, this is the structure. the copper pad module. They want to form it. This is the wafer to wafer bonding. All right. So when you flip it, it's copper, flip it, and anneal. So the atoms start to anneal and form it. And there's many intricacies. How do you deal with this kind of recess? All right. How do you form this gap? They are all very critical. And then how do you do the anneal? How do you clean the surface here so it will have a perfect bonding? By the way, this bonding is pure van der Waals compounding. It's not a chemical bonding. There's no compound form. It's copper to copper bonding. When you have two perfect same material together, even dissimilar material together, if they're super clean, they will immediately form a good bonding. Right? And look at that. This is the result they get. And using this text structure, they are doing electromigration. Okay, you see that this is the top copper pad, bottom pad. They form a nice bonding. And the result is this. No issue. Okay, no issue. They apply many learning from the CMOS world, and you have a copper recessed CMP with the low SICM surface roughness. You had to be very smooth. Okay, then you have a nice whip to wafer. So the mechanical requirement, surface roughness, is very critical. And that is actually where the challenge. It's not chemical or mechanical. So everything here, there's no, you don't form a funky layer and you want to try to adhere them together chemically. You are doing mechanical adhesion only. And the surface had to be super flat and super clean. And that is the challenge. Okay. And then the once they've done that electromigration, no problem. Okay. But let's not go to detail, but right now, published in 2022, this test vehicle, no problem. And with same wafer to wafer technology, 3D NAND reliability, okay. So this is 3D NAND people in China, YMTC proposed it. When they do their 3D NAND, they are not going to build super high stack of memory together like this. So what they want to do is put memory stack and CMOS stack on top of each other. The memory stack and CMOS stack now two wafer now. Remember, in the Samsung 3D NAND, they are same layer. I mean, same wafer. But for the YMTC, they are different wafers. All right, because this is to their advantage. And they could put it together with the bonding. So that's the end product will like be. And then, so this is wafer A, wafer B, and then we'll flip it and bond it. Okay, plasma activation, wafer to wafer alignment and annealing. So this is the typical packaging HBI process. You need to plasma activate it. I mean that you need to clean the surface, make it very, I would say, super clean, super smooth, even hydrophilic. They like to absorb, right? And the process is very important. And they do a pretty good job, I must say, because they achieve this submicron pitch. The VR pitch is very high, I mean, very small. The pitch density is very good. I think this is the best value I've seen. And but CMOS guy advanced packaging guy for CMOS like TSMC cannot do that yet. Why memory guy can do it? Well, there are two reasons. First of all, is wafer to wafer. The alignment for the whole 300 millimeter wafer to align together is much easier than what TSMC is doing with die to wafer, which I explain later. Okay. And let's look at results. So YMTC 128 layer and 232 layer die cross section, they could do that properly now. They align very nicely. 0.8 micron pitch, that's meaning a median interconnect, million per centimeter square, right? So you could think that way. So this is 2023 data, pretty nice. I would say pretty nice. Okay, technologically pretty nice. And this one shocked the world because that's barely below what Samsung can do. And they use a copper bond and bond two wafer together. Wow, very nice. Remember the pad alignment is not large. We'll talk about pad misalignment later. The pad misalignment is critical for EM reliability. A little bit off is fine. And we need to see how much is misaligned. That would be bad for electromigration. Okay. Just a quick note that the CEO of Chinese chip maker maybe stepped down. Is Simon Yang. Um, he's one of my Intel that co-worker. While I was in Intel, he's a integration guru, very smart, super smart guy. He figured this one out. Unfortunately, he has to go for, well, you know why. Okay, I don't want to go into detail. He resigned and he came back. Okay, D2W, die to wafer HBI is much harder than wafer to wafer. Right, the only company who can do it properly is called Besi, and they did it with TSMC on AMD product. Okay, all these products, the APYC, Ryzen, CCD, they are all doing that with hybrid bonding. The first company in large scale to die to wafer. Okay, so and Besi did it nicely with them. And it's a huge success for AMD, right? I mean, they claim they beat NVIDIA, you know, that's not going to detail. That's the huge success. And it's done by the first time using HBI in large high volume manufacturing, TSMC with it. And right now, Samsung and Intel try to catch up. They have not have this capability yet. And this is die to wafer. At the end of the day, you need to get the die and wafer to be super clean and no significant misalignment before bonding. Okay. And you're fine. Actually, electron migration is not a big concern yet. The question is why TSMC can do this way ahead of everyone else? That's interesting. These two companies has a symbiotic relationship, right? Symbiosis is like that. You coexist and benefit each other. That's what it means. TSMC benefiting from Besi's innovative solutions. It's called Vanguard pattern. That pattern is very unique. Okay. Besi, with a applied material gaining from the volume and technological advance driven by TSMC scale and scope. Now he owns the three-quarter world market in terms of die to wafer on HBI. But we still keep that in mind. TSMC is the head and Besi is a tail. What I meant is that the growth of TSMC is totally rely right now, totally rely on TSMC. Of course, you want to expand the market to say Intel and Samsung. And I know, and I am for sure know that this guy is going to work closely with Betsy to 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 enable the HBI. This one definitely much better than the current TCB that the other two are having. Right. But again, it's still that TSMC is ahead. Betsy is the tail. They follow the TSMC. And it's interesting to know that the Netherlands of Taiwan, Netherlands is Taiwan's biggest foreign investors, 10 billion NTD, 2 years ago. This investment because of the ASML and then this company. And Betsy is not exactly a Netherlands company, it's an Australian company, but Taiwan investment in Netherlands and I would say area around it is huge. It's huge. Just a side note, FYI. Let's look at Betsy's machine. It's a pick and place machine. And then it bought this company called Telecom 2004 to merge with the machine called Evo 2000. The pick, and this is an old machine. They bought the platform and improved the pick and place accuracy from 50 micron to 50 micron to 50 nanometer. Oh my God, that's really amazing, right? And this is critical. This is how they succeed and then leave the competitor in dust. And look at the spec. See that? This is a spec we introduced earlier, right? The enhanced capability uh, for this area. You have to have your hybrid bonding in a die corner area at 50, not to 500, of course, but 50 is the one you are going into, under Three Sigma control, right? So this one, they improved the machine from 50 micron to 50 nanometer. That's huge. Okay. And it had to be super clean as well. Okay. And additionally, they have a special patent called Vanguard alignment. This is their patent. And this one is kind of disruptive because it could place the die very quickly. And they claim the Three Sigma, it's 125 nanometer. And then they could do it in a 2000 unit per hour, right? I think it's been achieved. That's their goal. Okay. The innovation is that with a special alignment method, they could make a camera and the die in with a proper reference, and they would self correct and eliminate misalignment with this called nano actor, whatever that is. So they could put die quickly on top, very quickly. Talking about 2,000 uh, unit per hour with this machine is right now 125 nanometer accuracy. That's amazing. Nobody else can do that. Okay. And if you look at the recipe, right? EVG, I forgot to mention EVG. That's also an Australia company. It's dominated wafer to wafer. Besi owns the die to wafer, as we mentioned before, right? It's a TSMC POR. He owns the world three-quarter market already. And so this is a typical recipe. Before this recipe is put it on, the surface must be clean, a virtually atomic clean before bonding, meaning that it has to have a lower defect density and much stringent to the memory. And this one is what the 3D NAND is talking about. Why 3D NAND can do that and not here? In a NAND world, everything it's you know the pattern very nicely, and you could build many redundancy in these circuits, and therefore that's what all the memory is about. So the particle impact to yield is much less because they have a built-in redundancy. So if you fail a little bit in a hybrid bonding interconnect, it's okay. It's not too bad. They'll fix it. Okay, with their circuits. Okay. And that's the difference. But on luxury is not going to happen for die to wafer. Die to wafer going to be very strict. The defect density had to be low, much lower than the memories. And the wafer must be polished down to plus or minus 2.9, zero point 0.2 nanometer, the size of a silicon. Imagine you are picking up a small die about 1 centimeter square, putting on a 300 millimeter wafer, and then everything had to polish that flat, and that's a very big challenge. Okay, and what you do is that you have two-step annealing. Once you get your mechanically clean, low density, low defect density on all that, and then the super smooth, once you get it done, then you come up with temperature. So first temperature is about 140, 130 degree annealing for a certain period of time, and that's for your hybrid bonding to happen. A bonding happens in here, okay, in this oxide area, SiO2 roughly, or SiCN. But this is not done yet. And then you go to here, you go to raise to about 280 or sometime. That's when you have a metal bonding happens. Couples depend upon. Of course, before you have to have plasma activation, clean the surface, of course, for both. So that's two-step annealing. And that is the typical HBI anneal recipe. So you're talking about cleanness before you enter. And this part is easy. But difficult in a way, you need to make it fast. 2,000 units per hour. Okay. And then once you've done that, and then you go through the advanced packaging reliability spec, you follow this guideline, and then you've done your tests, they all passed. They passed the failure criteria, then you're okay. And for electromigration, for HBI, it seems no problem. It's no problem. Until and TSMC did that. The challenge is here. So the challenge is this part. It's mechanical handling part, not in the electromigration part, which is different from the CMOS world. CMOS world, the circuit is much denser, the line is much more narrower, and then the crowding effects are much more severe. And that's the typical part. Okay. So that conclude my talk. And I hope you get a good grip about what I'm trying to say here, that EM reliability is probably critical for tin-related bonding material, but not that bad for the copper hybrid bonding, as long as your misalignment is not too big. All right. Currently, it seems everybody can do that properly. And to introduce many design process tips that help you to become good at this field. And then talk about these two companies, TSMC and Besi, and the wafer to wafer and die to wafer, different challenges or different process technology relative to HBI, hybrid bonding interconnect. Thank you very much. That'll be all.